Mark Toth with RST Thermal. We're a manufacturer's rep company, and we represent about 10 to 12 different lines, all in the HVAC industry. My background is I've been in this industry in one form or another for the past 35 years, and I've been with RST now for about 13. My territory to cover for this position is New Hampshire and Vermont.
And I'm Karen S. Bushy. I'm a senior engineering consultant with VEIC, where I've been for almost 10 years now. And I've had an opportunity to do HERS ratings and help folks with design and verification for homes as a HERS rater. And then before that, I was a architect, so I was able to do a lot of design work for balanced ventilation systems. And recently, just a few years ago, installed a balanced ventilation system in my own home. So wanted to use that cumulative experience to share lots of learnings with you all. So I'm gonna get us started here with a little bit of like housekeeping type information, and then give it over to Mark to introduce the concepts of balanced ventilation. So this slide is really just included because we're going to be talking quite a bit today about the Vermont Energy Code. And we're just telling you that there's information in this presentation that is copyrighted by ICC because of that. So background for those of you who aren't familiar, the Vermont Residential Building Energy Standards that we like to, or I like to call ERVs. So if you hear me say ERVs, that's what I'm talking about. I apologize for that mashup, but that code is updated every 3 years, plus or minus. The most recent update went into effect July 1st of this year. So now applies to all residential projects, or the commercial version applying to commercial projects, but we're going to be talking about residential today. All projects that are starting construction from now on. There is a difference between the official ICC ERVs code book, which is the one that's shown in green on this slide, and the handbook. Neither of these actually have been printed yet for 2024. We're hoping to see them before too much longer, but you can go to the Department of Public Service website that I showed you on the last slide and use this link here to get to the latest versions, which, you know, have something to be desired still, but we're making the best of it. There is information there we can use. This presentation today is part of a 3-part series. So if any of you attended the Better Building by Design session that Mark and I did this past April, this is going to have a lot of repeated information from that. But what we heard from many people there was that we kind of sped through the information a little bit too quickly. There's a lot to cover with balanced ventilation. It's really hard to fit it into 1 hour. So for this, we decided to expand that time period a bit and dig in a little deeper on each of the subjects. So today we're going to be covering a lot of the background information and specific system design and sizing and selection of the unit for homes. And we're talking specifically about residential here, 1 through 4 unit buildings, and this also pertains to multifamily. When you're getting into multifamily, you have the option of either doing decentralized systems, which is 1 unit per apartment, which is really what we're going to be focusing on today, the smaller, like home-sized ventilation systems, not the larger centralized systems. There may be an additional training someday for that, but so part 2, we encourage you to sign up for. I think Bryn is going to put the link to sign up for that in the chat. And that is going to really focus more on the distribution system. So like ducting systems and, you know, how to lay that out and design that most efficiently, registers, location and selection, controls and maintenance of systems, as well as lots of other stuff. For part 3, we already have a date for that of October 17th. But what we're asking for that is for you to submit your questions and suggested topics that you would like to learn more about that we haven't covered yet. And then we're going to like compile, you know, the essential bits that you really want to learn more about into that session. So please, please, please email me. Don't forget the S in my email, because Karen Bushy in our finance department is not going to be very happy with us if you do. But please send your ideas to us, and we're going to put together a more focused session for that last one. So this is what we're going to be covering today. Some of the background information about why we're even considering balanced ventilation in homes. The differences between ERVs and HRVs and why you might want one over the other. System design, requirements, sizing, and recommendations for equipment selection. And these are the objectives that we've outlined for today, which I've pretty much mentioned. Just as a brief summary of some of the abbreviations and acronyms that we'll be talking about, I already mentioned about RBs. So CBs, similarly. There are some acronyms that I turn into their own words. So just wanted to give you a heads up what I'm talking about there. One is ASHRAE, American Society of Heating, Refrigeration, and Air Conditioning Engineers, which create some of the standards that we'll be talking about for sizing of systems and other aspects of systems. FIAS is another one that I turned into a word, which is the Passive House Institute US. We'll be talking about some of the passive house related standards for sizing systems. And I also just wanted to talk a bit about inches water gauge and inches water column, which are measurement units for static pressure, which will come into play more in detail when we talk about the sizing of units. And this really is, hold on, I'm trying to see my notes. So we're talking about the resistance in the system that the air has to overcome to reach its destination, the total external static pressure of the entire system, of the ventilation system. It's like the elements in the system which block or slow down the air.
Right,
they were going to
which
increase the static pressure. Go ahead.
Right, the T's, the elbows, the size of the pipe, all that comes into play with static pressure.
Filters, yeah.
Right, filters, exactly.
So that's an important thing to sort of like have an idea about as we go into this. And again, we're here because we're talking about this pretty major change which happened in the last update of the residential building energy standards in Vermont, which is requiring for all new residential construction, whole house ventilation, balanced ventilation system with minimum 70 SRE or sensible recovery efficiency and minimum 1.2 CFM per watt, which we'll talk more about. So I'm going to hand it over to Mark here to talk about balanced ventilation.
All right, feel free to ask questions in the chat as we're moving along. So why balanced ventilation? Go ahead, Karen, go ahead. So changes in construction and lifestyle practices have driven the need for us to rethink how air gets in and out of our homes. And when we look into the next few slides, you're going to see some examples of that. So back when people were living mostly in log homes and loosely constructed buildings, the old farmhouse here on the right-hand side of the screen, windows that shook in the wind, you know, no foundations in some case, fieldstone foundations in other places. We really didn't have a problem getting air in and out of the buildings. It's just something that happened naturally. But as we move along in time, we go, so even less than this. So as we moved along in time, we started using like pine boards instead of logs that had a tighter fit. Then we moved to plywood eventually, and plywood was much tighter than the pine boards. And now we're using these zip panels and taping the seams. Wall construction used to be a log, or then at one point it was a 2x4, and then it was a 2x6, and now it's a 2x6 or a 2x8 with multiple layers. Here you can see in the middle. I've been to houses that have, you know, you might have 6, 7 layers of construction materials before you get to the outside. Some places are even doing double wall construction. They're doing these foam enclosures that are pouring concrete into the foam. So walls have really changed. Insulation has changed. Real old houses, no insulation at all. Then at some point in time, you start finding in houses, you'll find crumpled up newspapers. You'll find hay, straw, old clothing, whatever people could find to stuff in the walls to help keep the house warmer in the winter, they stuck in the walls. Obviously, then eventually we moved to fiberglass and cellulose and ended up at spray foam. And basically, if you're spray foaming your attic and house like this one here in the picture is, and you're sealing up your foundation down below, you're basically taking this house that was breathing all the time, air moving in and out of it, you're turning it into a plastic bag. It's just not going to breathe at all. So as we move ahead here too, to look at the way we heat our homes. So back in the days when everyone had a fireplace, or many times houses had multiple fireplaces in their home. I always think about a house right around the corner from me here in New Hampshire where the house has 5 chimneys. It's a 2-story house. I'm assuming there's 10 fireplaces in that house. And there's a lot of old houses that look like that if you look around. Even in town, you'll see houses with multiple chimneys. When you're running a fireplace, it says here, I don't need to read this word to word for you, but between 200 and 600 CFM of air is moving out of the building. Now, just to clarify that, I know we talk about CFM. That's one of the things we've mentioned here this morning already. But a cubic foot, so 12 by 12 by 12. Imagine a box like that, 12 by 12 by 12 box. Imagine 600 of those piled up in a room. It's going to take up an enormous amount of space. That's how much air could be moving out of one chimney with one fireplace when that fire is really ripping. So that air is coming in through those loose windows and through that fieldstone foundation and through the walls where there's no insulation. These buildings just, we burn tons of firewood. And a lot of times, from a lot of things I read in the winter, people couldn't keep their houses above 45 or 50 degrees in really cold weather, even though multiple fires were running. And that's because there's all this ice cold air rushing in to replace what's going up the chimney. So it really was really inefficient, but those people didn't have to worry about fresh air in their home for sure. So as time moves by, we move to wood stoves and different wood burning devices where we restricted airflow with dampers and chimneys, and especially the wood stove. Now we can move as little as 10 to 25 CFM when we're in a full burn. Still, when you're starting up, you're still in that couple of hundred CFM with the door open and the chimney ripping to get the fire moving. But once we shut it down and get things burning correctly, we can be down to like 25 or even lower CFM. Now, back to that one for 1 second, Karen. So the fireplace, so wood stove did become a lot more efficient also. So that's why some of them show down to 10 CFM. If you have a catalytic stove, you can really, really turn things down. And the same we would include here would be a pellet stove. It's taking some air out of the building. Some of them are sealed combustion where they're bringing in outside air and totally sealed, so you're not using any air from the building. But this is a big deal because now with tighter homes, we may even need to provide makeup air for a wood stove. And we'll talk about that later on. So other heating systems we have in our homes, like the oil-fired boiler here, barometric draft damper there on the stack, that was always letting air move out of the basement for up to 50 CFM or maybe even more on a windy day. For anyone who has this type of heating system in their house, if you go down in the basement on a windy day, that flapper and that damper is just going to be swinging back and forth or sometimes pegged wide open because air, again, coming into the house from the wind and being sucked out the chimney, moving a lot of air through the house. Move ahead again. So what we've done now is we've gotten rid of the fireplace in most cases, gotten rid of the wood stove. Now we're getting rid of the oil boiler or propane boiler, moving to a sealed combustion boiler, just taking air in from the outside, burning the fuel, and then going directly out. So there's no air from in the house being used. We also have heat pumps. And basically what we're doing here is not letting any air for our heating system move air in and out of our house. So we went from a huge amount with a fireplace to basically with heat pumps now and high efficiency boilers to zero airflow. And the picture on the right basically shows we're enclosing ourselves in these buildings with no fresh air coming in at all. Other things that we have to worry about getting air in and out of house for, not just combustion, not just to keep us warm. There's all kinds of pollutants in a house. So look under the kitchen cabinets here. So under that kitchen cabinet, you have what you see there, cleanser, oven cleaner, all kinds of spray cleaners. That's all in your home. It is off gassing even while it's just sitting there. But that's not the worst part. when you pick up one of these bottles here, and it could be, 409 or Fantastic or whatever it is, and you clean your kitchen counter, you spray it down and you wipe it down with a paper towel, and now that cleaner is all gone. Well, it really didn't go anywhere. It's in the air. You dried it with the paper towel, but now the paper towel's in your house and it's going to evaporate off the paper towel. These cleaning products are in the air that we breathe in the home. And if we're not changing the air in the home, you're essentially breathing in what you just sprayed on the counter. There's no other way around it. Just like if you're cooking, if you cook something in the house and you're smelling it in the house, you're breathing that in, the combustion fumes, possibly from a propane stove, and whatever you're cooking, it's in the air. You're breathing it, just like the cleaning products. Condensation in a home is a very good sign that it needs to have ventilation, especially in the winter. If you drive by a home or in your own house, if you find in the morning, on a cold morning, your windows are all wet, great sign that that house needs to have ventilation. Also, mold in the corners of homes, mold above showers. Exactly, this is showing us that we have stagnant air in the house with moisture not moving. It's growing mold, things that we don't want to be breathing in. Next picture here is a garage. So this is a connected garage, like an under the house kind of garage where you see quite often. And what do we have in that garage? Just briefly, there you can see there's moisture on the floor. I see a pesticide sprayer. We see a motorcycle in the back. Obviously, we have tires, we have gasoline, we have oil. We have all sorts of stuff in this garage that we don't really want to breathe in. But when we close that garage door, that's a very leaky spot, most likely. So anything that's in that garage is going to make it into the home. So once again, if it's inside your building, you're going to be breathing it in. This is where we talk about, not too much today, I don't think, but I'll mention right now, if you use exhaust only ventilation, so you say, I'm just going to run my bathroom fan upstairs 24/7 to let fresh air come in the house. Well, one issue with that is we really don't know where that fresh air is coming from. And there's a good chance it's coming around the sill of the house, through the basement, or from the garage. So now we're essentially taking this garage moisture, chemicals, gasoline, tires, paint, whatever else might be in there. We're pulling that in through the house, through the kitchen, through the hallway, up the stairs, down the hallway, into your bedroom, and out the door, out the fan. So this is all in the home. We need to get rid of it. We don't want to be breathing any of this in. Oh, back one.
Oh, sorry.
The other big deal in all of New England is radon. So I don't know how many people in this session have tested their homes for radon, but if you haven't, I suggest that you do. If you look at this map, obviously a lot of Vermont shows orange. Some of the other states show yellow and orange in other places. But what I'm finding from research a little bit is that a lot of these places that show orange right next to the red, it's just that they don't have a lot of data from that area for one reason or another, and that radon levels are higher than you think they are in most of the country. So most of this map where it's orange should actually probably be red also. Radon comes out of the ground, it comes out of granite. We know that there's a lot of granite in all of New England. You get a lot of radon brought in when you build a house. You bring in crushed stone for under the foundation. You're bringing radon to your site. If you put granite countertops do off gas radon for forever. That's just how it works. I don't know the science behind the whole thing, but radon is embedded in granite and it continues to expel itself out. And like I said, including granite countertops. So it can be a big deal in a house. So why ventilate? So Americans spend 90% of their time indoors, and indoor air can be up to 100 times more polluted than outdoor air. It sounds kind of ridiculous, but if you think about outside and you think about inside, and we're using cleaning products, we have moisture from showers, we have, you might have hairspray and hygienic products, you're cooking, you've got all this stuff going on in your house, and if you're not ventilating it, literally could be 100 times more polluted than the outdoor air. And it's a perfect example of when it's a nice day out, we all want to open our windows. Everybody wants to open the windows in their house or open the windows in your car on a nice day because you get fresh, clean air. And so down on this list also, 30% of commercial buildings are affected by indoor air pollution. We used to hear a lot more about that in the past, like sick building syndrome and sick office syndrome. And this came to a head a couple of years ago with the whole COVID deal again, where you really have to understand if you're in a room with people, you are breathing the same air. That's why these meeting rooms and a lot of offices, even like at Efficiency Vermont, they have some meeting rooms there. When you go in a meeting room with 5 or 10 other people and you close the door, you're all breathing the same air in and out. So ventilation in those situations or a classroom is extremely important because we really don't want to be breathing each other's air in for multiple reasons. So poor IAQ costs the U.S. economy billions of dollars, hundreds of billions of dollars a year, just in people lost time that are sick, that don't feel good. Even if they're at work, they might not be productive because they don't feel good.
And I think I just wanted to add, I think this is like the thing to focus in on when you're trying to talk, building owners and clients into the added expense of a ventilation system, because, it is going to cost more than exhaust only ventilation. But,
Absolutely.
the health benefits are, and there's so many studies out there to prove this and so much research that's been done. It doesn't take a lot of searching to find some really helpful articles to prove your point. But I think, people are really concerned about health, and it's always something that rises to the top of the list. So I think this is what to bring out when you're trying to make that argument.
Right, exactly. So the picture down below with the students again, I've been involved in a few projects, most of them a few years ago, where we did some daycare centers, where we went, to the daycare center and they, I don't know, they keep 10 or 15 kids there during the winter. And the people that run the school would always say, every winter, people get sick. One kid gets sick, all the kids get sick. The teachers get sick. It's a disaster all winter long. People are sick because they're living in a poorly ventilated environment and sharing germs. Once an ERV was installed, we got a couple of these situations where basically someone would still get sick, but if that kid went home or didn't come in when they were sick, nobody else would get sick. The absenteeism rate and the sickness rate was reduced by like 95%. So this is a study they did in New York City. It's like 75,000 high school students. And they basically, without reading this to you, they have all kinds of facts showing that if schools have better ventilation, test scores are higher and there's less absenteeism. So the big thing is test scores are higher because people work better and can listen better when they have good ventilation. Even like I said, in these meeting rooms, the same kind of thing in a meeting room on the adult side of it. In a meeting room, if you go in there and you're sitting in there, everybody starts nodding off after half an hour, falling asleep. Well, we know that's because you're breathing too much CO2 in. And I have a CO2 meter that I bring in a lot of rooms with me. And if it goes over 800, it means you should ventilate. If it goes over 1,000, it means you really need to ventilate. And I've been in these rooms where in 15 minutes, it's at 2,000. It's at 2,500. And at the Efficiency Vermont Better Buildings Conference, I have that meter on my table always too. And if you're there next year, take a peek at it, because when I get there in the morning, the CO2 level in that big room is usually about 400, which is where it should be. When people start coming in, you see it creeping up, creeping up, creeping up. By the time the first session starts, it's at 1,000 or more. People leave the room to go to sessions, it drops right back down to like 600 or 700 again. And it goes up and down all day as people move in and out of that space. So
Yeah,
next slide.
thanks
Yep.
for mentioning about the air quality monitor, because I wanted to put something in this slide deck about that and didn't get a chance to. But this chart here shows actually the impacts of either air that's too dry or air that's too humid on health. So we're talking still about health here, and it just gives you sort of a range of 30 to 60% relative indoor relative humidity as a goal to have your indoor environment set to. And we'll talk a little bit more about how ERVs or HRVs can help or not help with that. But I think that a lot of people have a lot of concerns about this, rightly, and indoor air quality monitors are a really good way to, they're just getting more and more affordable. Just test your indoor environment, see, what you need, and if you should be concerned, maybe you have some concerns and you test your air and it actually doesn't look that bad, or maybe there are certain things that are higher, like the humidity, but the CO2 level is reasonable. It's just an easy thing to do that can really help inform you about next steps that you should take.
I think if you test your indoor environment in your home, you're gonna, like, I'm gonna say almost everybody will find that you're gonna be really surprised how poor the indoor air quality is in your home.
You're going to want to install a ventilator.
Absolutely. And even people that have a ventilator, you're probably gonna turn it up to run twice as much or turn the speed up to double what it is. Because I've been involved in
Wow.
a bunch of these things, and it's just amazing how poor the indoor air quality is, especially. And I'm a culprit of this. If you have a propane stove in your kitchen to cook with and you cook, your indoor air quality is going to be horrible. And the old thing on Thanksgiving Day, everyone falls asleep from eating too much turkey. Well, no, it's not from eating too much turkey. It's from being in the house for 8 or 10 hours with the oven on, and for the last hour before dinner, every burner on top of the stove running. That's why people are falling asleep. The CO levels in the house get so high that you will actually get really, really tired from cooking a big dinner for people. And there's 10 or 12 people in your house all breathing the same air on top of this. So the holidays can be very, very unhealthy.
Yeah, that's a good point. All right.
So balance heat. Oh, balance heat, or go back to one, please.
Oh, yeah, sorry.
That's fine. Balance heat or energy recovery. So we're going to talk about the difference between HRV, heat recovery, and energy recovery. So go ahead. So instead of just opening a window, we're going to use balanced ventilation. And the reason we should have mechanical balanced ventilation in a home is because you can't ventilate with windows, because you literally would have to be running around in your house all day, every day to do it properly and not over ventilate and waste too much energy. You'd be opening the back window over here for half an hour, 3 inches, opening one in front 2 inches, and then shutting these two. And as the wind changes outside, opening other windows, sometimes 6 inches, sometimes a foot. You'd be moving things all around. It's just not even feasible. So what we do is we figure out, by the space of the house and what's going on inside the house, like how many people and animals and what they're doing in there, we decide what CFM we need to keep that house healthy. So a balanced ventilation system, as you can see here in the picture, in the top left of that picture, you're going to see fresh air from outside coming in, going through this core, fresh air to the inside. And we're taking stale air out on the top right, bringing it down through the core and exhausting the air to the outside. So this core is the key to the whole thing. The differences between HRV and ERV is the core for the most part. We'll get into that a little bit. But what you're basically doing is running this air in and out, crossing it through a big heat exchanger of one type or another. And what we're doing in the winter is we're taking that very cold, dry air from outside, bringing it through that heat exchanger. Then on the opposite sides of that material, the warm, humid air is going out. And so we're going to warm the incoming air with the heat we've already made in the house. And if it's an ERV, we're going to slightly humidify that cold, dry air coming in. So we're going to take the outdoor air and warm it, make it more comfortable before we bring it in. And in the summer, just the opposite. If we're air conditioning the house in the summer, we're going to take that hot, humid air from outside coming in, and the cool, dry air is going to be going out. And we're going to dehumidify with an ERV and cool the incoming air. With an HRV, you're going to cool the incoming air in the summer, but not dehumidify it at all. So that's what we're doing in this core. And the balance means that in these type of machines, we need to have equal airflow in and out. I mean, you can vary it up to like 10%, but the key is to have it equal, because your core performance, no matter what machine you're using, is going to work best if it's equal in and out. That's how they're designed to work. If you have too much incoming air or more incoming air, you're going to try to slightly pressurize the house, and you're not going to warm it or cool it as much because you're coming through with more air than you're putting out. And if you have less incoming, it's just going to create a negative pressure in the house. So basically that's that. SRE and TRE. Karen, did you want to
Oh, sorry.
touch on those two?
Yeah, I'll just help define them. So the sensible recovery effectiveness, which is what the code refers to, is talking about the heat transfer between the airstreams, the efficiency of the heat transfer. And the TRE brings in the moisture transfer efficiency. So that's representative of total recovery effectiveness, which is a metric you only hear applied to ERVs. So HRVs are going to have an SRE, and ERVs are going to have an SRE and a TRE.
So I'm sure there's people on the Zoom here that there's some people are going to say, oh, I hear you're supposed to use an HRV, or I hear you're supposed to use an ERV, and you should never use the other one. We're going to kind of
I'm
dispel
just going to
those
go
myths here a
forward
little
to
bit.
that so we can just go right into that.
So it kind of alluded to it in the last slide, but so things with a heat recovery ventilator, HRV. So it transfers only heat and no moisture. It's not recommended for use in the summer with an air conditioner, because you would have to greatly increase the size of your air conditioner to handle that extra humidity coming in. So we're talking about, remember, 100 CFM is used for an average for a house, 100 CFM. If you're bringing in 100 CFM of 90 or 95% humidity air into the space with your air conditioner running, what's going to happen is your house is going to get cool from the air conditioner, but it's not going to be dehumidified. And you're going to have a very cold, clammy, cold, humid house, which is very uncomfortable. So that's one of the things there. And we're going to go back and forth on these two. An HRV also has to have a drain. It has to be in a space that's heated, and it has to be on a wall that's level. So this unit has to go on a wall in a heated space and have a drain so you can get rid of some moisture out of it because it's going to condensate in the winter. That's what's going to happen. In the summer, it will too, because of the air conditioning running. Most of them need a defrost cycle because they are going to freeze up in cold weather, and that core is going to turn to a block of ice. And then it goes into a defrost, which are multiple different ways the units can defrost depending on manufacturer. It's going to melt the core. The water is going to drain out the drain. It's going to turn back on and ventilate. And the reason it's getting icy is because we have warm, humid air going out and very cold air coming in. When you have a can here, if I take this koozie off my can, this can's going to get all wet on a humid day. And in the winter, in the HRV, that can gets wet basically and freezes. And this would turn all to ice. And we have to thaw it out because it won't have any airflow. So that is the HRV. The ERV, energy recovery, transfers heat and moisture. So as I said in the earlier slide, in the summer, we can use the ERV if we're air conditioning the house, because that cold, dry air going out is going to help to dehumidify and cool the incoming air, where the HRV is going to bring it in and we're going to cool the incoming air, but we're not going to dehumidify it. The ERV will dehumidify. In the winter, do just the opposite. So in the winter, we have moist, warm air going out of the house, and the ERV is bringing in cold, dry air. We're going to take a little bit of that humidity out of the outgoing air to increase the humidity in the incoming air a little bit. We're not going to keep the house at its humidity level. We're going to dry the house out in the winter like we need to, but we're going to do it in a controlled fashion. We're going to create a healthy indoor environment. The last thing we want to do in the winter also is to over dry a house, which can happen. And then we have all sorts of problems. You have cracked fingers, running bloody noses. You get zapped by the doorknob. Your woodwork in your house can start to crack. So we do want to keep the humidity under control in a house in the winter, but we do not want to over dry the house. So with the ERV also, you have no drain required, usually, depending on manufacturer, but usually there will be no drain required. You can mount an ERV in any orientation, whether we talked about the HRV had to be level on a wall in a heated space. The ERV can go on a wall, it can go sideways, it can go upside down, it can be on a 45-degree angle, it can be on the ceiling, you can lay it on the floor, and they can be in an unconditioned space. Obviously, any mechanical equipment is better in a heated space because it's just going to function better being in a warm space rather than being in a place that might be 10 below zero. But with the ERV, you have the ability to put that in the garage if you need, or in a crawl space, or in an attic if there's nowhere else to put it. And the HRV cannot be done.
I just wanted to state though that the energy code requires you to put it in conditioned space. So
Be in a conditioned
if you're
space, but
planning a new house anyway, don't
yeah.
consider putting it in your unheated garage.
So even if there's no space for it, if it's that you can create a conditioned space in a garage or an attic with an insulated box kind of thing to
Yep.
to make that happen if you need to. Just much more versatile. And the biggest thing is no drain. So the difference here really, I'm not sure what the next slide is if you want to move
It's
ahead.
this one.
No, okay, yeah. So the difference is the core material. The HRV core is always going to be either made out of plastic or aluminum. And that's why we get this wet can effect. And I mean, it's not even hot at all today, but this can, if I take it out here, this can's already wet just from the humidity in the air attaching itself to this can. And if it was cold out, if this can was really cold, it was winter, it would be turning to ice, and that ice would just build up, and then we'd have to thaw it out. The ice will build up, we have to thaw it out. Ice have to build up, thaw it out. If you're using the ERV core, what happens there is there's a little bit of moisture transfer, so we don't allow the ice to happen. And then at least the brand that I'm most familiar with, the ice, and we can take spikes down to 30 below zero without having ice form. So there's no defrost strategy needed with some ERVs at all. Another way to back to this last picture, the difference in the material happening, HRV would be like a rubber raincoat and ERV would be like a Gore-Tex raincoat, meaning that if you put on a rubber raincoat, if it's a thunderstormy day in the summer and you want to go for a walk, you're going to wear that rubber raincoat. You're going to be dry from the rain, but you're going to get all sweaty underneath and be soaking wet when you take that coat off because you're not breathing any moisture out. You're insulated by a barrier. The ERV would be like a Gore-Tex raincoat. I can go for a walk in the rain and not get all sweaty because my moisture from my body is going to wick through that material and get some air exchange in that coat and allow it to breathe. So that's a good kind of analogy of how the two cores work. So there we go. We got a little ahead of myself with the HRV core. Again, either aluminum or plastic. The air is going to move through the core and we're going to warm it and we're going to cool it depending on the application, but there's going to be no moisture transfer whatsoever. So that's why you need the drain. The ERV core, most of them are a static plate for residential. There are other types. There's desiccant wheels and there's other types commercially, but 99% of everything residentially is going to be a static core. And this, I talked to someone yesterday about this slide. You'll see this latent energy transfer via diffusion, different percentages there. Those percentages are just put in this slide for an example, because when you have an ERV core, the transfer rate of moisture versus heat is completely dependent on the application of that particular moment. It depends. Is it 60 outside and 70 inside? Is it 90% humidity out and 50% inside? Or is it 0 outside and 100 inside because the wood stove's on? It's a sliding scale. You never have the same amount of humidity transfer or heat transfer. It just depends on the two static points that you pick. And I'll show you a tool later on that you can use to find out what your true performance is at any actual time of day in any weather condition. So where and when to use ERV or HRV? So we recommend at RST Thermal to use an ERV in every application in New England, except for places where you have extremely high humidity. Like I would talk about like an indoor pool, an indoor swim spa thing, a steam room, anywhere you have extreme moisture. So if you were going to do this and you were doing a pet shop and they've got, 50 fish tanks in there that are always wide open and just the humidity in there is just crazy. Well, that's a better application for an HRV than an ERV. The ERV manages moisture in spikes. We're even great in locker rooms and in like a gymnasium type environment. We can take that humidity and get rid of it. But if it's going to be 24/7 extreme humidity, HRV is a better choice. And either one, you should never use either one in a very dirty or a toxic environment. If you have to wear something, a mask, like a respirator, to go into a building because the the solvents they use or the glue or whatever they're using in there is so potent it'll burn your lungs. You shouldn't use an ERV or an HRV that I know of. There may be some you could, but generally a residential ERV or HRV would be destroyed. The materials would be destroyed by that stuff that would destroy your lungs. You need to be able to breathe the air. And the dirty meaning that we don't want to put this in a place where there's tons of dirt in the air. So let's say it's a woodworking shop and there's sanding and grinding and there's just dust in the air everywhere. And everyone in there is wearing a filter mask so they don't breathe in all the sawdust all day. All that's going to do with either of these products is clog the filters and make them not work properly. So we have to really look at the application. And it's important to remember that the ERV or the HRV is not make-up air. So I can't tell you how many times I've gone to a new house and I walk in and I'll see this, 8-burner Viking stove with this 1200 CFM hood over it. And I'll say to the people, I said, well, or I'll say to the contractor, what are we doing for makeup air for this exhaust hood? And they'll say, oh, nothing. There's no makeup air for that. Well, then I look around, the house is spray foamed. You've got, high dollar windows in the house. It's not going to work. You have to have makeup air for something that's going to remove anything more than 400 CFM out of it. That's the code, I believe, 400 CFM and up. It just won't work. That's the problem. The people spent thousands of dollars on this thing. They're going to turn it on. It's going to pull a suction on the house. It's going to sound like it's running, but it's going to be like sucking on a plastic bag with a straw. There's nothing to take out. Sure, you've all experienced that. If you ever go to a Japanese restaurant where they cook on the tables, like on a Friday or a Saturday night when it's busy, you walk up to the door and you can't open the door. It's like, it's sucked shut from all those big fans running. You open the door and you kind of get sucked into the building. That's because they don't have enough makeup air. That's the same thing that can happen in a house. An ERV or an HRV will not do anything for that. So like I said, you can unbalance these up to 10%. So if you have 100 CFM HRV or ERV and you unbalance it by 10%, well, now you're going to bring in 10 CFM extra. 10 CFM is absolutely nothing if your hood is 1,000 CFM. It's not going to do anything at all and shouldn't be thought of that way. If you have an extremely tight house, you may even need a makeup air unit for a small range hood, a clothes dryer, a fireplace, or a wood stove. There's a lot of cases I've seen in new construction where even a fireplace or a wood stove will not draft because there's not enough air in the house to make that happen. So we need to look at it. And also, it is not a humidifier or a dehumidifier, and it's not a whole home air cleaning device, meaning that this unit or these units will dehumidify and they will humidify depending on the circumstances. But if you need a humidifier, an ERV or an HRV is not a humidifier. Or if you need a dehumidifier, they are not a dehumidifier. I've had a few calls this summer from people that, I got a customer that's got very humid air in their house. They want to put an ERV in. I said, well, is the house air conditioned? No. Well, the ERV is going to do absolutely nothing for a house that's not air conditioned because we're not going to be able to dehumidify. You're just going to bring in outdoor humidity. And both of them, in a lot of cases, will make the house more humid inside because early in the morning, I've been watching my humidity thing here a lot of times in the morning. You might be at 90 or 95% humidity first thing in the morning. And if you had an HRV or an ERV running without the air conditioner on, you'd be pumping that moisture right in, just ruining the indoor environment even more, making it more humid than it even was. And although these units have filters on them, they are not whole house air filters. The filters are in place basically to keep the core clean. The filter on the outgoing side is 100% there just to keep the core clean from any pollutants like hair and dust that might get into the core from your house. And the incoming air filter is on there basically to filter out any bugs or pollen or dust off the road or whatever else might be coming in from outside. So they do have filters, but they are not whole house air cleaners by any means. So should we integrate bathroom ventilation with an ERV or an HRV? I see it done a lot. I see probably at least 3/4, half to 3/4 of the new homes they get involved in, they are using our ERV products to ventilate the bathrooms. And that is a great way to do it a lot of times, especially if you think about it in the winter when you are creating very warm, very moist air in the bathroom, and we're going to expel that out. It's going to give you very warm air to use to warm the cool air coming in on that core material. So you're going to get a really good change there in the temperature of the incoming air. And also, you can run all of your ventilation, all of your exhaust would then come from your bathrooms, whether it be 1, 2, 3, 4, however many there are. And you would just bring fresh air into other points in the house, being the bedrooms, the living room, wherever you're spending a lot of time in the house, and you would just create your ventilation system that way. You can also use dedicated bathroom fans. I think this one here is an interesting one because whether it's an ERV or an HRV, these things need to be maintained and kept clean. This fan that you see a picture of here, this is like a 2-year-old apartment building in Burlington where I went because supposedly the ventilation wasn't working well in this building. I went with a contractor and we went into a couple of apartments and this is what the bathroom fans looked like. And that is like 90% closed up. So if that's a 50 CFM fan, it's probably running at like 10%, like 10 CFM, if that, because they're so dirty. So anything that you're going to use here is going to need to be maintained and kept clean. And then there are multiple ways to control bathroom ventilation. And we're going to talk more about that in the controls next time, but we'll touch on it right now, being that you can have it so that it's always running, whether it be a fan or an ERV. You could have constant ventilation in the bathroom. You can have constant ventilation with a boost when you come in, or you can have the unit be off and have it turn on when you come in. But if you do, the control system needs to be kind of tailored to the homeowner and how involved they're going to be. You can do a button. So when you walk into the bathroom, every time you have to push a button, and whether it be, for 20, 40, or 60 minutes, you have to push that and manually turn it on. If you don't turn it on, it's not going to do anything, obviously. Same with the bathroom fan. You have to flip it on or it's not going to turn on. There are other ways to do it. You can do humidity sensors. Well, if you do a humidity sensor in a bathroom, it is, going to work when you're taking a shower, but it's not going to work for any odors or, cleaning products that you're going to use in that bathroom or hygienic products, a hairspray or whatever. You're not going to exhaust that. You can do VOC sensors, but a VOC sensor is going to turn on when you use a hairspray or deodorant or whatever, but it's not going to turn on when there's high humidity. So lots of different ways. And then the last one that comes in a lot of times, how about a motion detector or a occupancy sensor in a bathroom, which is definitely a good way to do it if people aren't going to turn things on. But the problem with those is that if I have a motion detector in my bathroom to turn my ERV on or my fan on for 20 minutes every time there's movement, well, a lot of times I'll walk by the bathroom and just grab a Kleenex or whatever, or put something on the counter. And then you just walk in, grab a Kleenex and leave. Now the fan's going to run for 20 minutes, really unneededly, possibly. So there's a lot of different ways to look at that. And I kind of think you have to look at the particular house and see what's best for that application.
Yeah, I just wanted to jump in. And one thing I really prefer the method of integrating the bathroom exhaust with the ERV system. I know there's a lot of differing opinions about that out there. People thinking, oh, there's no way that low ventilation rate is going to exhaust the moisture out of my bathroom, which is why the boost switch is a really great idea. But the thing is, if you have an exhaust only, even if you have in addition exhaust only fans in the bathroom, like that's taking that moisture that you've created in your house and exhausting it to the exterior. And especially in the dry winters that we experience in Vermont, like it's a really great idea to be able to recover that moisture and put it back into the indoor air and distribute it throughout the house. It's actually a more healthy environment. So by using exhaust fans at the most moisture producing time of that room, you're kind of wasting that moisture, which could be really helpful in the home. That's the
Right,
way I
because
look
that
at it.
home, you may get a call from that homeowner if you didn't do it the way she's talked about, you may get a call at some point that that home is too dry inside and they need a humidifier,
Right.
where this will take care of both of those things.
So I'm going to talk a little bit here about design requirements, and I'm going to try to distinguish between what's required by the energy code and what's recommended, because the energy code, if anyone's had a chance to look at the ventilation section, it's a little bare bones, I think. There's a bunch of information that was actually, it appears that it was taken out from the last version. So I'm going to try to do my best to clarify like what's actually required and what's just recommended. But the question really is, how much fresh air is enough? And honestly, like even the experts don't agree about this. And there's 3 different options that code gives you for determining your minimum airflow rate. But basically it's a balance. So, you know, in theory, you couldn't have too much fresh air, right? But the thing is, it takes energy to deliver that fresh air. So there is an energy penalty with using a higher airflow rate. So you want to balance that fresh air need with the energy use. So the energy use is including the motor, you know, the energy that the motor is using to deliver that air to the space. And, you know, no unit is 100% efficient for heat transfer efficiency. So you're always going to be losing some energy through delivering that air to the space, and your heating or cooling system is going to have to make up for that. So that is something that's important to include in any energy modeling that you do for the home. And of course, we mentioned before, you know, too much airflow could actually over dry the home.
Well,
So
I'll comment on that too for a second, Karen. As we spoke about yesterday when we were looking at these, every building has different needs. Every house has different needs. Just because I'm involved with a lot of sizing, because people will call me, well, I have this many square feet of a house. What size unit should I use? It really depends so much on what's going on in that particular house. You could have a 2,000 square foot house and there might be one person living in there. That same 2,000 square foot house could have, you know, a mother, a father, grandparents, 3 kids, 2 dogs, and 4 cats. It could be one house of 2,000 square feet might need 3 times the ventilation of another house of the same size. So you really got to look at each situation individually.
yeah, maybe we'll have time to dive into that a little bit more in session 2.
Right.
I just realized that it's 9:26. We have till 10 o'clock to do this, and we're about halfway through here. So I might have to speed through some of this. I apologize. But basically, the 3 options that code allows for sizing your system is the RBs, or what we call the prescriptive option, the ASHRAE standard 62-2019, or passive house ventilation requirements. And I'll dive into those in a little bit more detail upcoming, but the important thing to keep in mind is the minimum 70 SRE and the minimum 1.2 CFM per watt, the heat transfer efficiency and the motor efficiency that is being required by code. And you can find more information about those in the Home Ventilation Institute information, which I will dive into it more in a few slides. 920 is basically the procedure that they use to test and list all of the data for these units. And 911 is the directory of all of the units. So that's what that means if you read that in the code. And you can, so for package plus points option for compliance in the Vermont Energy Code, there are quite a few points available for going over those efficiencies. So you can get 3 points for either an 80 SRE or above, or 3 points for 2.0 CFM per watt or above. And that's either or. You can't take those both on top of each other. I'm going to clarify here. Actually, first I'll talk about room specific rates. So the code doesn't talk a lot about what's required for specific rooms. We're going to talk more about what's recommended in some upcoming slides, but just note that it does have a minimum for the bathroom exhaust. So if you are including the bathroom exhaust in your whole house ventilation system, especially if it's an ERV, you want a minimum of 20 CFM. That's minimum, but is it really enough? A lot of people would argue that you really want more than that to sufficiently get the moisture out during a shower
I'm
or
just
other
gonna use,
moisture events.
I want to use one real quick analogy there. All these minimums, none of them are enough. Everyone's familiar with interstate, that Route 89. The minimum speed is 45 on that road. It's not enough, right? That's not what anyone wants to travel. You shouldn't be traveling 45. It's not enough. So any of these minimums really need to be looked at as that way, not what you're shooting for, but what you have to do, at least to even stay there.
Yeah, we'll be talking a lot about minimums in the next slide, so that's a good thing to keep in mind. So the one thing that I think was added in one of the more recent revisions, because I don't remember seeing before, but all the systems must have provisions for circulating the air to finished living spaces. That's how it's defined in the code. And they mentioned that that can be done by distribution ducts, undercutting doors, or installation of grills, transoms, or equivalent means. And I think I'm going to leave diving into that a little more for the next session because there's a lot that we could dig into there for the non-ducted distribution. But yeah, that's like a whole other topic. Just interesting to note that there is a requirement for that now. So we're going to distinguish between rated and verified. Those three methods of calculating your minimum airflow for your ventilation unit that I mentioned, there's only one of them that's rated. So and then there's three others. So Arby's has either rated or verified option, and then the other two have to be verified. But you're designing your system before the home is built, right? So you're kind of guessing at what the verified amount is going to be. And as somebody who has verified a lot of these systems over the last 10 years, I can tell you that they almost never test. The verified number is almost never what the rated number is. So, and there's a lot of reasons for that, which we're going to go into in the next couple sessions. So I am actually a fan of using the rated capacity here just for your initial sizing. So we're going to look at that. So rated in the Arby's prescriptive method is telling you need to use 25 CFM per person, and the person number, this is like based on ResNet and probably other requirements. It's always bedrooms plus one. So if you're calculating the number of people in a home, you're going to count the number of bedrooms and add one. So we're going to use this 3-bedroom, 2,000 square foot home example for the next couple for these three methods. And 25 CFM per person gives you a 100 CFM minimum rated capacity. And this is correlated to the HVI listing at 0.1 inches water gauge, which if you remember that's external static pressure measurement, which is a very low static pressure. It's very little resistance in that ventilation system. And then I pasted a copy of the prescriptive chart that is listed, or table that's listed in, this is actually from the handbook, but a similar one in the code, which you can easily refer to for the building you're working on. And the verified capacity is less than that because when you verify it, it's not going to be as much as the rated capacity, especially at 0.1 inches water gauge. So that one's CFM 15 CFM per person, which works out to be 60 CFM verified. And you can get an additional point for the package plus points method by doing the testing. That applies to any of these that need to be tested. So for the ASHRAE standard, this is a little bit higher. Actually, I think most cases you'll find that the ASHRAE calculation is going to be your highest verified airflow rate. So if you're trying to get as low as possible, don't use ASHRAE. But that's also looking at the, so for ASHRAE, the calculation is 3 CFM per 100 square foot occupied space plus 7.5 CFM per person. So with this 2,000 square foot 3-bedroom home, we're looking at 60 CFM for the square footage plus 7.5 times 4, 30 CFM for the people. So we get a total of 90 CFM continuous ventilation rate without an infiltration credit. So the one thing to note with the ASHRAE standard is you can basically you can subtract out the air that comes into your home through leaks in your home, which Mark talked a lot about very early on in the presentation. That's how we used to ventilate our homes way back when, before they were airtight. But you have to use a blower door tested, air leakage number. So again, you're not going to have that until the end of the project. So it's hard to really, know what exactly that's going to be for early sizing. Plus, I don't really want the leaks in my home to be part of my ventilation system for all of the reasons that we just mentioned. So I probably personally would choose not to take that infiltration credit.
Yeah, the
So
problem
then,
with real briefly, the problem with the problem with the leaky house is that on a day when there's no wind, it doesn't leak at all. On a day it's really windy, it leaks way too much, and there's no way to control it.
right, no way to control it. And then also to note with the ASHRAE standard is that it does have the same bathroom requirement, and it adds a kitchen ventilation requirement, which can be either intermittent or continuous. And that's not required by the Vermont Energy Code, but it is required by Energy Star if you're going for that like current federal tax credit that's available. So this tool is a pretty great way to easily calculate that ASHRAE flow rate. You can find it at this link once we send the slides out. And it's actually was recently, I think, purchased by the DOE or it's DOE or EPA, and they're transferring it to like the Building America website in the coming months, hopefully not too long, and hopefully updating it for 2019. But this should still get you the information that you need, and you can actually put in here your tested air leakage of your home to find out what that infiltration credit is. For this example, I used 500 CFM for the air leakage, and that gave a credit of 20.9, which you can see in the second line to the bottom, which subtracted from my 90 CFM gives me 69.1, which I rolled up to 70. So I'm going to use 70 for that number for this example. Another thing I wanted to point out here is if you do have a system that's not running continuously 24/7 and it has like a control that allows it to be like, 40 minutes on, 20 minutes off or something like that, you can actually use this dwelling unit ventilation runtime solver that's part of this tool and put in your target target fan capacity or the design airflow, and it'll tell you how many minutes per hour that unit needs to run in order to achieve that. And then Mark's going to introduce this tool.
Yeah, so this is by one of the manufacturers. Renew Air has this on their website. If you go to the Renew Air website, click on CORES, CORES. There's a whole bunch of different things you can do there. But what I want to show you here is this ERV calc that Karen has highlighted there, that button. You would go to ERV calc and do this calculation by ventilation zone. And what this tool does, if you look down below here, Karen, can you show right in the middle where it says ASHRAE standard right there? So you can click that down. You can find 2016, 1999, 1990. It goes all like all the different codes that have ever been through. You can choose whatever code you want to look at. And then you basically go to zone details. And we're going to talk about houses today. So we're going to put number of people. We'd put 4 in here, and we can put area occupied, 1,200 square feet. And we're going to push that button. Well, first we have to go to category. So this is residential and dwelling unit we have here. So if you go in these categories, there's every category in there: residential, educational, healthcare, restaurants, stores, offices, all kinds of stuff. Then a subcategory of, even more narrows it down. And it's going to use those categories with the ASHRAE standard that you chose to give you this ventilation rate. So we go to the zone detail and say 4 people, 1,200 square foot house. Click on that. Right below, it's going to give us what CFM we need for that building. It's really a fun tool to play with because you can change it. You can say, okay, so one person in a 2,000 square foot home, it might come out with 80 CFM or something. But if you put 6 people and big dogs, so we're going to call it 6, 7, 8 people in a 900 square foot home, it might come out with 350 CFM. And you can really dig in here and change the categories and look at different applications and different numbers of people and different square footages and just see how drastically the ventilation recommendation changes depending on how many people are in a space and what's going on in a space.
And contact Mark if you want to walk through that
Yeah,
with him,
I can
because it
walk
can
you
be a
through this.
little, like all the inputs can be a
Absolutely.
little confusing. And our contact information will be at the end of the slide deck. So for the third option, the passive house standard, they allow you to add up your supply requirements and add up your exhaust requirements, and you take the largest of either one. For most cases, that's going to be the exhaust. And it's interesting here, they have these minimum flow rate requirements for each room to add up and get your result, but they also have a recommended for each one. So we're like, why don't they just make it the recommended, make the recommended the minimum, but
Right,
alas,
right.
this is the way it is. So we get a total of 45 CFM for a 3-bedroom home. And then for the 2 bathrooms in the kitchen, we get 65 CFM exhaust, which obviously is larger. So we're going to use that in our example here. So 65 CFM for passive house. And we're going to, those required or recommended rates that I just showed you, those are going to come in when we're actually doing an example in a couple slides. So comparing all of these 3 standards that I was talking about, we get the 100 design or rated CFM. And then for all of the 3, we have 60, 70 or 90. I'm going to use 90 or 65. So you can see there is quite a variety there. And the question still remains, what is the right amount? So let's look at how we might like design the actual space.
Right.
And
Yeah,
add
so
those up and see if they meet the 60 or the 90 or whatever.
right. There's all kinds of different ways to design duct, and we're going to get more on this next time too with integrating or separate duct systems. But what has to happen is you have to get fresh air into the building and stale air out of the building. It wouldn't make any sense to do that with a supply of fresh air here and 2 feet away a suction, because all you're going to do is short cycle. The idea is to get air spread out in the house as much as you can. You want to put fresh air into bedrooms, living spaces where you spend a lot of time, like a family room or a den, and if you might work in an office all day. So where you're spending the most time, put fresh air, and we're going to get air out of places where we create heat, moisture, and odors. They're all listed here: bathrooms, kitchens, laundry rooms, mudrooms, exercise basements. So get rid of air out of places where we're making bad air and put it in where we're spending the time. We don't want to do it the opposite, because we don't want to have places where we're creating moisture and odors and drag that through the whole house and into your bedroom and then exhaust it from there. Let's get rid of it where it's being created and keep the fresh air where we're staying. And
And
as far as
also,
go ahead.
sorry, go ahead.
No.
I
So
was
as
just
far as,
gonna, I was gonna say like 1 port per room is sufficient. I've seen folks think about these systems more like heating and cooling ducted systems where
right.
they're designing like a supply and an exhaust in each room. You don't need that, just exactly what Mark was just talking about. You want the air to be to kind of move around the home on its own. So supplying in the areas where you're spending time is putting that fresh filtered air into your breathing space. And then you're exhausting from the moist air spaces which are creating odors and moisture. And so that air is naturally moving through the home and creating the airflow and distributing that filtered air throughout the home.
Right. Right.
And
So in some applications, it all depends on the application. So if you have an application, there's a family that doesn't have any money, but they've got some health issues, you need to get fresh air in the house. You may only be able to get 1 supply and 1 exhaust in that house. My recommendation is get them as far apart from each other as possible and try to keep the exhaust in the place, the dirtier side of the place or the more humid side of the house, and put the fresh air in near where the person that's having the health issues go on. Air moves through a house. Right now I'm in the attic. I'm in a finished attic of my house. 2 floors down, if my wife was right now gonna make cookies, right? I'd smell them come out of the oven in 5 minutes. That means that the air is moving through this house, even without fans and everything else. The air is moving in a house. So if you're putting fresh air in it's going to move through the house, especially if you're exhausting it from somewhere else. A beautiful day like today, you go and open one window on one side of the house and one window on the other side of the house. By the time you get home, the air is going to be fresh. You don't have to have it open in every single room of the house to get fresh air in. And we're going to dig into more of that next time.
Yeah, and the reason on the last slide I was saying don't go crazy was because these rates can really add up. So if you're putting, one port in every room and you're adding all these rooms up, it really can add up. I'm going to show that on the next slide, but here's just some examples of rates per room to start with. These are more, the passive house exhaust. If you're doing passive house, obviously you need to follow that, but the EBT guidance here on the lower left corner, this is just, recommendations for the most part. The bathroom is going to be the only one that's required. And then this chart here is from a passive house with a unit that actually had a low, medium, and high speed. And it was designed to run on the medium speed. So we were using sort of those passive house target rates. And here I wanted to just stress that you're looking for a balance, like was mentioned already, but also re-stressing, you want to try to approach equivalent exhaust and supply. So you're going to add up whichever side is going to probably be the higher total. And then you're going to take, which is usually exhaust, and then you're going to take the supply air spaces and you're going to basically like fudge around with them until that total of those adds up to what your exhaust is. And so it's a little bit of a puzzle and requires a little bit of maneuvering of numbers till you get the right thing. But there are cases, and maybe we can get into this more next time, where you might want to usually it's a pressurization, I think, of the home, slight, but it never should be more than 10% difference between the total of the supply and the total of the exhaust. You should be aiming to achieve pressure equalization in the home. The system should not significantly affect the air pressure in the home. I'm going to go
Yeah,
on.
I've been in some classes where building scientist people have strongly recommended against pressurization of any significance, because if there is moisture in the home, it can actually drive moisture into the leaky points of the house, and then it will freeze, and you'll have moisture in the walls that could actually freeze in the winter and create all kinds of problems.
Yeah, it's just a really good idea to aim for that pressure equalization, I think. So for this example, that same 2,000 square foot 3-bedroom home, on the example on the left, I'm adding up all of the exhaust ports and the supply ports. And I used sort of like the bare minimum of what we would typically see for a new home. So you want the exhaust in your kitchen and your bath, of course, and you want to supply air to all of the living spaces. So we get a total of 84 CFM for minimum design airflow. And you can compare that to what we were seeing before with the 60, 70, 90 CFM. It's in that range of the 90, I guess. So if we decided, hey, actually, I would like a extract in the laundry room, and I have this fitness space in the basement, we should put an extract down there. And actually, I would like, my open office space at the top of the stairwell, I'd like a supply there. And, maybe this also open dining room. So you can see that can really add to your total, and you're probably going to be looking for a larger unit in that case. And the reason I mention open space, because like we were talking about before, the air kind of like just on its own working its way around the house. If it's an open space that doesn't have walls and a door, maybe it doesn't need its own supply. It could be someplace that you could use to sort of save money. For ductless units, you need to take all of the pairs. If you're talking about this type that I'm showing the photo of here, they work in pairs. So one of the two units is bringing in fresh air at the same time that the other one is exhausting, and then they switch. So as the pair, that amount of air is considered the supply because they work in pairs. So the way I've seen it, like one could be maybe 15 CFM on a medium speed, which is a reasonable speed volume wise. But you need to add all of those up to get your total capacity. So if you're aiming for 60 CFM minimum in a home, and you're expecting to run it on medium and it only gets 15 CFM on medium, you're looking at, 4 pairs of these
Which
units,
means
which would be
8
8
6-inch
holes.
holes inside your house. Yeah.
So just an example to show that we think that these systems do have a place, but it's in smaller open homes, and, sort of larger single family homes, it might not be the best fit, especially in new construction, because you can actually put ductwork in there. So we got like 12 minutes left here. We haven't taken a single question, which I feel really bad about, but I'm going to try to speed through this last section because I feel like it's maybe one of the more important parts, and we can review it in the next session if we need to, if I've gone too fast. But let me try to at least tell you, this I feel like is maybe one of the most important things that we're going to talk about today, which is oversize your ventilation unit. We're not going to tell you to do that for your heat pump. Don't oversize your heat pump, but oversize your ventilator, because there's many reasons actually, but I think maybe the top reason is because it's going to be quieter. It's going to be quiet and people,
Running anything at a lower speed. If you have a big unit running at a lower speed, it's going to be a lot quieter than running a small unit at its top end.
yeah, these are not designed to be run at their maximum speed. So I think a lot of people go to select the unit looking at that capacity and saying, okay, I need 100 CFM in this building. That's a 100 CFM unit. That's the one for me. But you don't want to run that at 100 CFM. And plus, you won't be able to get a higher speed on it if, for example, your ductwork doesn't come out very well and it has a high static pressure and you're not actually testing that much air at the ports.
Yeah, you might only be getting at 80, and now you're stuck with what you bought. If you have one that's bigger and can be adjusted, you have room to play, room for changes. Maybe you're only one person in that house now, but maybe a year from now, there's 4 people in that house. You can adjust for the future.
Exactly. And then also the filter is going to get clogged up and it's not going to deliver as much air like as you go along. So our guidance is to size the ventilator so it's delivering your designed airflow at 60 to 75% of its max capacity. So you can do that by taking that design airflow and divide it by either 0.6 or 0.75. So down here, I did that, and we're going to use the lower of that. So 133 CFM is about the target that we're going to look at for this example. And these are just stating all of what we just said. It's going to be more efficient. It's going to be quieter if you're not running it at top speed. It's going to be more efficient for a couple reasons. The motor isn't going to be running as hard, and it's going to have better recovery efficiency because the air is going to be moving through the core more slowly. Did I get that right, Mark?
Yeah, you're going to have a larger core with the air moving through it slower. So you're going to get much better energy or heat transfer because we're not blasting it through. It's going to have more time to spend in that material transferring its energy.
Yeah. So you're going to want to start with the Home Ventilating Institute, which I mentioned earlier. You can get to it through this link or just go to HVI certified products. Section 3 is the section that's going to talk about ERVs and HRVs. 1 and 2 are more about like exhaust. One of them's exhaust only, one's kitchen, I think, or something like that. Oh, and they redid this website like a month ago and has never worked very well since. I'm really hoping it's going to be fixed soon. But I'll just start by showing you like this bar up here is on the main landing page. Once you go into the directory, you're going to see a whole bunch of ERVs and HRVs listed under each other. I just snipped one for this example. You can filter it by manufacturer, brand. You can filter it by ERVs and HRVs. And then you can just take a look at what's out there. It's a really, really handy reference because it's going to show you the rated supply at 0.4 inches water gauge, which is a little bit, it's going to be a little bit lower number than what the code is telling you to use, which is 0.1, but I'll show you where you can get that. It's going to give you the max SRE at 0 degrees Celsius or, freezing at 32 degrees Fahrenheit, which is what you're going to use to select the efficiency per code. It's going to give you the airflow at that SRE, which you can tell right now, 66 CFM right here is quite a bit less than the supply it's giving you at 0.41 inches water gauge. And then the max power consumed at that SRE. And this is something that they added with that update, which is great. they give you the CFM per watt motor efficiency here. So you can use that also to verify that the unit is meeting code. Now, if this works, hopefully, I haven't checked it this morning. Yesterday, it was still not working. You can click on this model details button right here, and it pops up all these really helpful tables where you can dig into more information about the unit. This is the message that I was getting the last couple of days. So I really hope they fix this soon, because you can actually download spreadsheets of this information and get it that way too if this button doesn't work, but it's really hard to sort through. It just takes a long time. So the table should look something like this, and it's going to show you how at the different external static pressures, you're getting different airflow rates. So this is the number that code is telling you to use, 138 CFM. For this example, this would be fine. This would meet code. We got the 138 CFM, which is well above any of those requirements, which would give us a little room. And it's meeting it's well above the 1.2 CFM per watt efficiency. So we're good there. But I just wanted to point out how the airflow rate decreases with the increased external static pressure. This unit actually doesn't look that bad, but other units, like you'll see an even more dramatic drop off with the increased static pressure. And I'm just going to go to the next slide. This is another chart that you can see through that model details window that's giving you even more efficiency, view into the efficiency. So we're going to look at these top two lines, which is showing you airflow rates and their associated efficiencies at different airflows. The 66, if you remember, was the rate that it was telling us the max SRE is associated with. So 66 CFM, which, that still would technically, if we were able to verify the system at 66 CFM, that would meet our minimum flow requirements for most of those requirements in the code. So that actually would be pretty good. And then we could run this unit at a low speed. We'd be getting good efficiency and good motor efficiency and heat transfer efficiency. And we're using 35 watts, which is really relatively little. But if something were different and say, our duct system didn't come out as we designed or something, and we ended up having to bump that up to get the airflow, then that external static pressure that I was showing you on the other slide would make it so that we're using a lot more energy to deliver that air. And if we needed to bump up the airflow, you can see how that impacts the wattage, not even double the amount of air, triples over 3 times the amount of the power needed to deliver that air. And then your CFM per watt just plummets. So I just wanted to point that out. And that applies to the cooling rates as well. Here you can see the TRE drops from 66 to 56 with that increased airflow. Okay, so all of that was talking about 70 SRE and 1.2 CFM per watt. I also wanted to point out that Efficiency Vermont has incentives for residential new construction, so new homes built by an EEM member. So if you are a member of the EEN residential builders or another EEN member, possibly reach out to us because we have some pretty nice incentives available for efficient units. We have to go above and beyond what code is requiring. So our requirement is 75 SRE, and I think it's 1.7 CFM per watt or above. And the reason is that for that is because we're asking for an ECM or variable speed motor in the units that we're incentivizing. So 75 SRE, ECM motor, cold climate rated, and the way you can search for those units is going to this link on our website, and you can see all of the units that meet these requirements, and we would be eligible for the incentive. So if you have more questions about that, please reach out to me. And we can also help with design and verification. So we're happy to help with any of those things. And Mark,
so
do you want to talk about this?
Real quickly, if you're looking at a unit and you see an advertisement or something, if it sounds too good to be true or it looks too good to be true, it's probably not true. The difference with ERVs, HRVs compared to other heating equipment, if a company makes a boiler or a furnace, they need to be sent out for verification of their efficiency. With ERV, HRV, the manufacturers do their own testing. So some of them aren't completely honest in their testing. Like some manufacturers will test a 300 CFM unit at 300 CFM and give you the rating, while others may test a 300 CFM unit at 50 CFM and give you that rating. So it looks like it's much more efficient than it really is. Also, always use a piece of equipment that has been listed by HVI. There's a lot of things in the country now starting to show up from China and other places that are being built by companies that we don't really know what materials they're using, and we don't know a lot about these equipments coming in. So just use something that's been tested and listed so that we know that is a safe piece of equipment to use. But once again, just if it looks too good to be true, it's probably not true.
Yeah. And then I think we can take any questions that there might be for the next couple minutes. We don't have very long, but the last couple slides are just talking about some of the brands that we're actually seeing out there. And if you're seeing ones that are other than these, please let us know, because we are always trying to find out what's happening out there in the field, and you know, distinguishing between sort of like typical standard passive core units, and then some that actually combine with heat pumps. And here's some ductless options that we're seeing out there as well. Interesting products. And then these tips, which I think maybe we'll start.
We can start with that next time.
Start with that
But
next
there's
time.
something to say about the different manufacturers too. Like, there's a lot to talk about still. Like, how much, if you buy something that's lower price or more expensive, what are you really getting for that kind of thing? So I think we need to start there next time.
Yep.
To continue our equipment selection thing for a few minutes.
Yep. So we're up on time. I just